Hello, this is the section 3.10 lesson. In this section we're going to introduce the idea of approximating the binomial distribution with a normal distribution. The practical significance of this section was probably more important in the days before calculators and computers, but we're still going to see applications of this idea come up in chapters 4 and 5. So the central result of this section is theorem 310.1, which says let x be binomially distributed with parameters n and p. So then as n approaches infinity, the distribution of x approaches a normal distribution with mean np and a variance np times 1 minus p. So this is a result somewhat similar to the central limit theorem. So informally, what this theorem is saying is that x, this binomially distributed random variable, is approximately normally distributed with this mean and this variance for n, quote-unquote, large enough. Now, like with the central limit theorem, we had a rule of thumb for how large n had to be for this approximation to be reasonable. And here in this case, the rule of thumb says that np needs to be at least 5, and n times 1 minus p also needs to be at least 5. Okay. So as an application of this idea, let's take a random variable x that's binomially distributed with parameters n and p, and y be a normally distributed random variable with mean np and variance np times 1 minus p. So then the probability that x is between a and b is approximately equal to the probability that y is between a minus a half and b plus a half. Okay. Now, the justification for why we add and subtract a half is given graphically in the book. But this idea of adding and subtracting a half is what we call a continuity correction. The reason it's called that is because x is discrete, whereas y is continuous random variable. And so when we go from a discrete random variable over to continuous random variable, we have to make a little correction there. So that's done by adding and subtracting a half to those limits inside of this probability. So as an example of this idea, suppose an airline has a policy of selling 375 tickets for a plane that seats only 365 people. That's called overbooking, and this is a common practice in the airline industry. Records indicate that about 95% of people who buy tickets for this flight actually show up. Find the probability that there are enough seats. Okay. So, in other words, there's going to be enough seats if 365 or fewer people show up. So we want to find the probability that this happens. So let's define the random variable x to be the number of ticket holders who show up. So we sell tickets to 375 people. Each person is a trial. Each person either shows up or they don't. And there's about a 95% chance that any one single person shows up. So in other words, x has a binomial distribution with 375 trials and a probability of a success of 0.95. So then in terms of x, we want to find the probability that x is less than or equal to 365. So to apply this theorem, let's define the random variable y to have a normal distribution with a mean of n times p and then a variance of n times p times 1 minus p. And if we do all that arithmetic, we get a mean of 356.25 and a variance of 17.81 people. Okay? So this number right here tells us that we would expect about 356 people to show up, which is obviously less than the 365 seats that we have. So that kind of helps to justify the logic behind this idea of overbooking. Okay? But we're interested in more than just the expected number of people who show up. We want to find the probability that 365 or fewer people show up. And so using this normal distribution, this is the probability that we want, and we're going to approximate it by finding the probability that y is less than or equal to this number 365 plus a half. Again, we need to add that half for the continuity correction. Okay. Well, now y has a normal distribution, and so to calculate this probability, we convert this number over to a z-score by subtracting the mean of 356, dividing by the standard deviation. We do that arithmetic, we get a z-score of 2.19, and if we look up that probability from table C1, we get our final result of 0.957. So there we go. We got about a 98% chance that there's going to be enough seats available.